In this lecture, we'll discuss the existence of uncountable sets. And the method we'll use to prove a set is uncountable is known as Cantor Diagonalization. So before we do that, let's just recall what we mean in the first place by countable or uncountable. So a set S is considered to be countable if, and there are two cases, remember. So the first is if S is finite. All finite sets are countable. Or, second case, one we're really going to be interested in, is if it's infinite, but it has a bijection with the natural numbers. So we can write that like this. It has the same cardinality as the natural numbers, meaning there's a bijection. That's what this notation means. It doesn't mean counting the elements. They're infinite sets, so you can't count all the elements of natural numbers, for example. This just means we have a bijection. There exists some bijection between your set and the natural numbers. Okay? And uncountable, I mean, it's exactly what you think it is. It just means it is not one of these, meaning it's infinite, so it's not finite, and there exists no bijection to the natural numbers. Okay? And in the previous lecture, we were having a hard time actually finding uncountable ones. We were coming up with bigger and bigger sets. It turned out they were all just in bijection with the natural numbers. So the question we considered at the end was maybe all sets are countable. So are all sets countable? Essentially, is there only one kind of infinity? Sort of the philosophical question, I suppose. And the answer turns out to be no. And in fact, there's a very familiar example that you're all aware of, and it's the real numbers. So the real numbers are uncountable. So R is uncountable set, meaning you cannot ever find a bijection from R to the natural numbers. Now let's go ahead and prove this. It uses this technique of Cantor Diagonalization, named after the mathematician Cantor. And in fact, we will even prove, so let's prove the following proposition. The interval just between 0 and 1, so the real number is just between 0 and 1, even that is uncountable already, let alone all the real numbers. So even if we just considered a small interval from 0 to 1, just all the real numbers living inside here, that already is uncountable. And here's the idea. So the proof, well, let's think about what we need to prove. We need to prove that there does not exist. I suppose first we need to prove it's infinite. That's pretty obvious. You can find infinite sequences in here. For example, 1/2, 1/3, 1/4. So to prove it's uncountable, we would actually need to show that there does not exist any bijection from S to the natural numbers, or from this interval to the natural numbers, and that seems like a fairly tall order. How can we show that there's no such bijection? Maybe we're not imaginative enough to come up with one. And so when you're in that situation, often you want to try a proof by contradiction. So for the sake of contradiction, it's hard to prove directly. We want to try contradiction. And the reason is, what would it mean if we contradict this? It'll mean, suppose there is a bijection. So suppose there is a bijection from my interval 0 to 1 to the natural numbers. Let's do it. Let's have it go the other way. So let's go from the natural numbers. It doesn't matter. But let's just go from the natural numbers to 0, 1. The reason it doesn't matter is because the inverse of a bijection is also a bijection. But let's suppose we have a bijection from the natural numbers to 0, this interval. And let's actually list it out. So as follows. remember, when we have a countable set or a function like this, that is equivalent to just being able to list out the elements, right? So I can say, like, here's my function. I'll have an n, 1, 2, 3, 4, 5. I'm going to tell you where that natural number goes. Let's say 1 goes to, well, make a little table here. Let's do that. And in this column, I'm going to put the real number between 0 and 1. And what are real numbers? I mean, they're essentially infinite length decimal expansions. Don't have to repeat or anything. So this will be f of n. So let's say my first one is 0.a1. Actually, no, I'm going to need to fill this whole grid. So let's give it 2 indices. So a11, a12, a13. These are just the decimal places, right? A16, etc. That might go on forever. And if it doesn't go on forever, let's just make it go on forever by adding zeros to the end. That doesn't change the number. So if it terminates, if it's like 0.25, let's just add zeros after it. So we have an infinite length decimal expansion for every real number. Okay, and then we'll write out our second real number here. And we'll start with 0 point because they're between 0 and 1. And then our third one, 3, 3, A3, 4, A3, 5. I don't want to go on forever here, but I do want to give you enough rows here to show you the idea. It's a very geometric argument. So we're going to be using this grid here. A5, 5, 2, sorry, A5, 3, A5, 4, A5, 5. You get the idea. So for the sake of contradiction, we're supposing there is a bijection. Here's that bijection. Okay? And this goes on forever. But it's a list. So it is a way of listing them. And we're going to prove that you cannot, in fact, do this. So there's going to be some contradiction that arises. And here was Cantor's idea. The contradiction is going to come from the following. So we can actually create a number. We can find a number, a real number. Let's call it x. That's in the interval from 0 to 1. That does not appear on this list. Okay, so first we list them out. And we can now find one that does not appear anywhere on the list. Okay, and that is, the idea is Cantor Diagonalization. That's what it's called now. It's a very beautiful argument. So the way it works is, you're wondering, what is diagonalization? So you go down the diagonal in this picture. So for the first digit of my number x, I'm going to build this number x. So for the first decimal place of x, of this number x, well, what digit am I going to choose? I'm going to choose, I'm actually going to look at this number here, okay? A11, the first decimal digit of the first number in my list, and I'm going to change it. So I'm going to choose any digit other than A11. Okay? And I have plenty of choices, so I can always do that. There are 10 possible digits. And then you continue in the following manner. So for the second digit, choose any digit other than A22. So you go diagonally. That's the diagonalization. So I look at my second number to find a second digit of x, to choose a second digit of x. I'll look at my second number in the list and alter its second decimal place. Okay, and maybe its first decimal place will match x, right? But I know its second one won't. So essentially, that's the idea, and you keep choosing in this manner. So etc. So what do I mean, etc.? So for the, let's write it out. For the ith digit, choose, so of x, choose any digit other than AII. So for example, for the 100th digit, I would go down to row 100 in my table, look at what that real number is, go all the way to its 100th digit, and change that. Okay? That way, I can create this X, ensuring that it's not going to be anywhere in this list. That's the idea. Okay? So that's the conclusion. Yeah, so X cannot be on the list. Let's really convince ourselves of that. So this is a somewhat tricky argument. So it cannot be on this list. Very clever argument as well. And again, so we're going down like this. This is a digit. This is a digit we're altering. Okay. Why can't it be on this X? The reason is the ith place of X differs from the ith place of the ith number on my list, so of fi, I suppose. Okay, that's why. So if you come to me and claim, oh wait, X is in position 257 on this list, I can say, no, it's not, because it can't be, because if you go down to row 257, look at the 257th decimal digit, then that's going to differ from X. And that's, by the way, where this X is constructed. So it cannot be on this list. Okay, and that is the proof. That is the idea of Cantor Diagonalization. And before I conclude this, I do want to point out, this is actually not complete. There are a couple slight issues with this argument, and so I want to actually show what those are. Slight issue, number one, let's call it. It's really not a big issue at all, and we'll fix it. But here's the problem. The way it's written here, this is not correct, and it's because what if I somehow end up choosing 0.00000? Let's say there are never zeros along a diagonal, and I just happen to choose 0 because it's the first digit. Okay, well, there's a slight problem. 0 is technically not in this interval. It's not in the open interval from 0 to 1. Okay, so I just need to make sure. That's easily fixed. I need to make sure I don't choose the number 0.00000, etc. Okay, at some point choose something non-zero. That's super easy because, again, as I pointed out, we have many choices in each step. So let's actually immediately modify this. So there are lots of ways to do this. Probably the simplest way is just say choose any digit other than A11 or 0, right? So just avoid 0 in every step, and then we'll be fine. Okay. So that fixes that issue. There's another issue which appears pretty serious at first, but still actually just a very slight issue. But what that issue is not every number, not every real number, actually has a unique decimal representation. Surprisingly. You might not have thought about this, but here's an example. Let's say 0.6399999 repeating, all nines after that. Well, what is that? That is the same as the number 0.64. It's kind of like a 0.99999 repeating. It's just the same number as 1. It's just two different ways of writing that number. So occasionally we'll have two different ways of writing a real number. And that'll be, it turns out the only case where that happens is this one, where you have an endless string of 9s at the end. In exactly that case, we have another way of writing it, just by sort of replacing all 9s with 0s and bumping up this next digit here. Okay. Or, alternatively, anytime we have a terminating decimal expansion, we can write that instead with infinite sequence of 9s at the end. Okay, so wait, how do we fix this? Well, if this is the only problem where you can get this infinite sequence of 9s, why don't we just avoid the digit 9 as well? We can do that easily because, again, we had 10 choices. So now I guess we have 9, 8, 7 choices. That's still plenty of choices. I guess we had 9 choices here, and now we have 7. So we'll just always avoid 0 or 9. Turns out, you can even just like sometimes the way this proof is written up is, if the digit is 3, then choose 4. Otherwise, choose 3. So you only really need 2 digits. But yeah, let's just avoid 0 and 9. It makes it easy. And these are really the only 2 issues that arise. So otherwise this is a complete proof. So this set is uncountable. And I guess the philosophical implication, you have to be a little careful with this, but there are infinities of different sizes. That's a really interesting thing to think about with this argument. And I'll put sizes in quotations because this is often misinterpreted. So what exactly do we mean by sizes? Well, what we mean by sizes is in terms of the cardinality we define. So bijections. That's how we compare sizes of infinities. Does one infinite set have a bijection with another one? If so, we say they're the same size. Okay. So that's exactly what we mean by sizes. Because again, you can't count the elements. It's an infinite set. And then a corollary of this argument, corollary meaning something that follows from the proposition, is that R itself is uncountable. Okay. And it's because R contains this essentially, but to really show this, let's find a bijection from R to this this interval here, and that's actually a little bit tricky if you think about it. But there's some nice functions that can do that. So actually, so R is actually the same cardinality of this interval. Here's why. So consider this function. We'll define a function from 0 to 1. To the real numbers, and will be defined by, here's the idea, we're going to use a function from trigonometry. This is one that often comes up in these arguments, so it's a good trick to remember here. The tangent function. So what does tangent look like? It's something like this, and it has an asymptote here. So it's vertical. Asymptotes at pi over 2 and negative pi over 2. And what you can notice here, so it's tangent x, what you can notice is, tangent will map this interval, pi over 2 and negative pi over 2, onto the entire set of real numbers, right? Because this goes off to infinity, this goes down to negative infinity. And as you can kind of see by the graph, it's 1 to 1 as well. It's injective, right? Any horizontal lines meeting it just at one place over 2. This is you can create a bijection from here to here. How do you actually do it? Well, we have a bijection from this interval, negative pi over 2 to pi over 2, to the real numbers. So why don't we just map 0 to 1 onto that interval there? So how would I do that? This interval has length pi, so I need to scale by pi first of all. So my x, I'll multiply by pi to go from 0 to 1 to 0 to pi. Then let's just subtract pi over 2, and it will take the tangent. Okay. And this is a bijection. It's a bijection from 0 to 1 to r. So not only is r uncountable, it in fact has the same cardinality as just this interval. And in fact, any interval. Essentially, yeah, you can probably figure out how to make that work. It's the same kind of argument. You can just map that interval onto 0 to 1 and then use this tangent function. Okay, excellent. And one other thing I just want to point out is that the set of irrational numbers, so the set of irrational numbers, what are irrational numbers? Essentially, that's just r minus q. So it's all the numbers that aren't rational but are real. So they have decimal expansions that go on forever without repeating or without terminating. And q are the ones where the decimal expansions are repeating or terminating. And so what about the set of irrational numbers? Well, that's smaller than r, right? That is smaller than r. It doesn't include any of the rational numbers. But that's also uncountable, okay? So set of irrational numbers is uncountable. And a proof is, well, how do we prove something's uncountable? What do we do here? We contradicted it. So we tried to contradict it. So let's suppose, and let's just give it a name. Oh, I guess we can call it r minus q. So let's suppose a set of irrational numbers is countable. Then the real numbers I can express as a union of two countable sets. Is q union, so things in q or the things in r minus q. And in fact, this is a disjoint union. These two don't have anything in common. But yeah, q is a union of, so is a union of two countable sets. But a union of two countable sets, a union of two countable sets is countable. Why is that, by the way? Let's sketch that really quick. So why is it when you take a union of two countable sets that's countable? Well, suppose A is one of them, and for it to be countable, remember, that's a very tangible thing. It means we can list out the elements. And let's suppose B is the other one, so B1, B2, B3, B4. Okay. So we've got two countable sets, and then the idea is, so we're kind of using some strategies maybe from the previous lecture. How would we list out all these elements? Well, again, the thing you're not allowed to do is say just list out all of A, then list out all of B. Why can't you do that? You'll never finish listing out A if it's an infinite set. So you do something like interleaving the elements. You alternate. So we can write out A union B like A1, B1, A2, B2, A3, etc. Okay. And I suppose technically these sets could have some elements in common, but maybe if we get to anything that's in both of them, you don't list it twice. So that's the idea. So a union of two countable sets is countable. And what does that contradict? Well, this was what we were supposing, right? We're supposing our the set of irrational numbers is countable. For sake of contradiction, we got our contradiction. And so, and what was the contradiction? We found that R is countable when we have already proven that it's not. So the set of irrational numbers, really, irrational numbers make up most of the real numbers in some sense. So like the real numbers, you can just imagine as, I don't know if it's a Venn diagram. just imagine it's all this space here, and then the rational numbers are just a tiny point. It's just a tiny speck in there, and the irrational numbers are far more numerous than the rational numbers. So that's sort of the picture to have of the real numbers. Okay, that's it for this video. Thanks for watching.